Hello once again, grade 10 science fam. It is me, Sir Ramon, and today we are discussing gas stoichiometry, or just a complicated term for trying to figure out how much gas you have involved in a chemical reaction. Now, of course, we already discussed what gas is. So again, it's a state of matter where your particles are moving around randomly, okay? And they have a lot of kinetic energy. Now, when we say stoichiometry, you guys might have forgotten what that's all about. But when we say gas stoichiometry, we're combining the ideal gas law with stoichiometry. So let's focus on the word stoichiometry. It means measuring the amounts, specifically of our reactants in a chemical reaction and the products of a chemical reaction. So every time you have a chemical reaction, take note that it's always written with an arrow that shows the trend of the chemical reaction, whether it's going from one side to the other, and the ingredients are called reactants, and what you make after your reaction are called the products. So again, stoichiometry is just measuring how much reactants you have and how many products you have in a chemical reaction. Very simple conceptually speaking, but when we start calculating, it gets a bit complicated. So stoichiometry has four basic steps that should be in the readings you should have read before you watch this video. So again, four main steps. The first step is to balance the equation. And the second step is from mass to moles. We have to convert. The third step is to use what we call a mole ratio from the balanced chemical equation in order to get the number of moles of the other compounds, and finally converting the moles back to the mass. Again, it allows us to get the mass of the reactants and products if we're given just the moles or the mass of another reactant or product. So let's have an example so we can refresh our memory about stoichiometry and gas stoichiometry. So again, in this case, this is already an example of gas stoichiometry. So at 1 atmosphere and 27 degrees Celsius, how many grams of carbon dioxide are produced if we burn 24.63 liters of methane? So again, if it's a gas stoichiometry question, we need to use both ideal gas law and stoichiometry. But the question is, which should we use first? Okay, so in order to figure out which one we use first, again, we have to take note of these concepts. Again, in stoichiometry, we have the step going from mass to moles. Whereas in ideal gas law, we already have N, which stands for the number of moles. So one of the key differences between stoichiometry and ideal gas law is that stoichiometry has mass starting out, whereas ideal gas law has moles in its formula. Okay, and ideal gas law also has the quantities volume, pressure, and temperature. All right, so in order to figure out if we use stoichiometry or ideal gas law first, remember this: when your mass is given, again, if you're given mass usually in the unit of grams or perhaps kilograms, again, those are units of mass, you do stoichiometry first because stoichiometry can allow you to convert from mass to moles. But if you're given P, V, or T, again, pressure, volume, or temperature, those are quantities that describe best our gas. So we should use, our ideal gas law first. Now, when you're given moles, that's actually not a gas stoichiometry question because both our ideal gas law and our stoichiometry have the number of moles in their formula. Again, we have moles here and moles here. So both ideal gas law and stoichiometry involve moles. So if you're given moles, you have to look at what's being asked for in order to figure out if you do just stoichiometry or just ideal gas law. Okay, so going back to our example problem, we were given 24.63 liters. And liters is a unit of volume. So we use ideal gas law first, or PV is equal to nRT. Now, if we get our given, again, when we use our GAPSA format, we start out with our given. If we get all of the numbers from our given from our problem, we have 180 m. which is pressure. We have 27 degrees Celsius, which is temperature. We have 24.63 liters, which is the volume of CH4. So we have our given pressure, temperature, and the volume of CH4. Again, the volume of CH4 is given, but what we're solving for, what's being asked for, is actually our number of moles of carbon dioxide. So again, we have a chemical reaction. Again, it's asking here if we burn CH4. So that is actually a chemical reaction where you combine CH4 with oxygen to create carbon dioxide and water. Again, combustion or burning is when you combine a certain organic compound with oxygen in order to produce carbon dioxide and water. All right? So before we do that, again, we use ideal gas law to get the number of moles of our CH4. Again, we need the number of moles of CH4 first. So if we use our ideal gas law formula, we get 1 mole of CH4. Again, we didn't need molar mass or anything to get the number of moles of CH4. We just needed the pressure, volume, and temperature, which were already given in the problem. So after ideal gas law, next we have to perform stoichiometry. And in the first step of stoichiometry, we need to balance the equation. And so step 1 balancing, that involves balancing the number of atoms in each element. In the reactants, again, in the ingredients, each element has to have the same number of the number of atoms in the product side. All right, so what does that mean? Again, if we go back to our chemical reaction, again, if we burn methane to produce carbon dioxide and water, we have to add what we call coefficients to our compounds. Again, this is just balancing chemical equations. When we add coefficients, we're trying to make sure that they have the same number of elements on each side. In this case, if we look at carbon, we have 1 carbon here. We can see that there's only 1 carbon here on the left side or the reactant side, and 1 carbon here on the product side. So carbon has no problem. However, if we look at our hydrogen, we have 4 hydrogens here on the reactant side and only 2 on the product side. What number can we put here to make this 2 equal to the number of hydrogens on the other side? Okay? In order to make 2 equal to 4, we need to multiply 2 by 2. Again, 2 times 2, we get 4. Okay, so that gives us 4 hydrogens on the product side. All right, so we're good with the hydrogens. Now let's check our oxygen. We have 2 as a coefficient here. Wow, okay, sorry about that. We have 2 as a coefficient here. So that means that we have to do 2 times 1 for our oxygen on the product side. So 2 times 1 is simply 2. So we have 2 oxygens here and we have 2 oxygens there. So all we have to do is to retain this number of oxygen if we just look at this oxygen. But we also have another 2 oxygens here. So we have 2 plus 2. There's 4 on the product side. So we need to have 2 oxygen molecules on the reactant side so that we get 4 oxygen here and 4 oxygen on the product side as well. So when we have our balanced equation, we have 1 CH4, 2 oxygen molecules on the reactant side, 1 carbon dioxide on the product side, and 2 water molecules on the product side. Now take note that we don't have to write coefficients of 1. They are actually invisible. It's understood that your coefficient is 1 if you don't write it on your compound. So once we have our balanced chemical equation, we can actually get our mole ratios. These are simply conversion factors or fractions that say how many moles of one compound correspond to how many moles of another. So how do we get that? We just look at the coefficients of the different molecules. For example, here we have methane, CH4. How many moles of methane are in the balanced equation? We can see here that there's no number, so that means there is 1 mole of CH4 in the balanced equation. Now, how many moles of oxygen are there in the balanced equation? If we look at oxygen, again, just the oxygen molecule, we have the coefficient of 2. So we have to write that there are 2 moles of oxygen in your equation. So that gives us our molar ratio for methane to oxygen. You have 1 mole of methane for every 2 moles of oxygen. On the other hand, if we have the comparison between oxygen and carbon dioxide, once again, our oxygen has 2 moles, as you can see over here. And your carbon dioxide has just 1 mole because there's nothing written there. Alright, so we just write 1 mole here. This just means that there's 2 moles of oxygen for every 1 mole of carbon dioxide. And finally, in the last molar ratio for our examples, we have 1 mole of carbon dioxide made for every 2 moles of water. And again, we're just copying the coefficients that we see in the balanced chemical equation. So if your balanced equation is not actually balanced, if you get your balancing wrong, everything else that you're doing is already wrong. Okay, that's why it's important to show me the steps of your solution so that I know where exactly we went wrong. Alright, so moving on, step 2, we have to convert from mass to moles. But we don't need to do that since we already have the number of moles. Again, we have 1 mole of methane. And 1 mole of methane from our conversion earlier using ideal gas law. So we skip immediately to step 3 using the molar ratio to get from number of moles of methane to the number of moles of carbon dioxide. Now, again, we had 1 mole of CH4 and we have to convert it to 1 mole of carbon dioxide. So if we look at our mole ratios from our balanced chemical equation, again, if we look at CH4, we have nothing there, so its coefficient is actually 1. And for carbon dioxide, it's also a coefficient of 1. So our molar ratio is 1:1. Now we get to use our dimensional analysis in order to convert your 1 mole of CH4 into carbon dioxide. But since it's 1:1, again, we just cancel out the units and we're left with the unit that we want, the moles of carbon dioxide. So again, we just have 1 mole of carbon dioxide. But the question, again, what's being asked for is the number of grams of carbon dioxide. We're not done yet. We need to convert from moles to mass. Again, in stoichiometry, we want the amount, and amount is expressed in mass. So we need to convert the number of moles of carbon dioxide into grams of carbon dioxide. And to do that, we need the molar ratio. In order to get the molar ratio, you guys will need a periodic table or at the very least the molar mass of the elements which are given here. So if C is equal to 12 and O is equal to 16, all right, we have 1 atom of carbon in carbon dioxide and 2 atoms in oxygen. So we have 12 and 32. All right. And if we add 12 and 32 together, we get 44. And that gives us our molar mass for carbon dioxide. For carbon dioxide, there are 44 grams for every mole of carbon dioxide. Again, when we get the molar mass, it's simply the number of grams per mole. So, since we have 44 grams per mole, we can use that as a conversion factor in dimensional analysis. So we start out with our mole of CO2. We multiply it by the molar mass so that we can cancel out the unit. And we get the number of grams of carbon dioxide, which is simply 44 grams of carbon dioxide. Again, the final answer is that there are 44 grams of carbon dioxide whenever we burn 24.63 liters of methane at this specific pressure and this specific temperature. Alright, so again, that's been a sample problem for gas stoichiometry. I'll be releasing a problem set, which includes 2 to 3 word problems about gas stoichiometry. And this time, even though it's counted as a quiz, you guys can work together. You guys can ask each other. And of course, you can always ask me. PM is the key, but my dad's right behind me. Alright, so it's time to cut this recording short. I'll see you next time, guys, and good luck on your problem set. Goodbye.